Hello students, this is Ms. Howman and we're going to go over the math vocab. This is log number 2 and you will be turning this in for a grade. So make sure you've got all the words down as well as all the examples. We're going to be doing 6 vocabulary words, but we are going to use 7 spaces because number 2 is going to take up 2 different spaces. So let's begin. Okay, our first word is equivalent. And if you notice, it looks kind of like equal. At the beginning, there's an equi. So it kind of tells us something close to equal, but not exactly. So our definition is equal to or corresponds with another in value, amount, function, or meaning. So if we wanted to say it was equal, we just say equal. But in this case, we have to use equivalent. So equivalent is different from equal in that it looks different, but it still means the same thing. So our examples should help kind of make sense of this. First one is going to be the U.S. President and the U.K. Prime Minister. So our U.S. President is the leader of the executive branch. He doesn't have all the power, but he's kind of the leader of the country. So the equivalent in the U.K. or in England is called the Prime Minister. So it kind of has the same deal. They are the leaders of the executive branch, and if you wanted to say, oh, take me to your leader, like if you're an alien, you're going to bring them to the Prime Minister. So the U.S. President and the U.K. Prime Minister are equivalent roles. They may look different, they may have slightly different functions, but they're still equivalent. Okay, my next example is a Big Mac is equivalent to 5 bananas and half a cup of broccoli. So this has to do with their amount of calories. I'm pretty sure you're thinking, okay, a Big Mac is absolutely nothing like 5 bananas and half a cup of broccoli, but it turns out that if you eat one or the other, you're going to be consuming 540 calories. So they are equivalent in the fact that they both have the same amount of calories. They look different, they taste different, but they are equivalent if we're talking about calories. My next example also involves a Big Mac. Okay, so we just said a Big Mac is equivalent to 5 bananas and half a cup of broccoli, but that's when we're talking about calories. However, when you go to McDonald's to get a Big Mac, you pay them $3.99, and we're not including tax in this. But you're also saying when you're buying something and you're accepting that price, you're saying this is worth whatever I'm paying. So when you pay that $3.99 for a Big Mac, you're saying this is equivalent. So that Big Mac is equivalent to $3.99 if we're talking about money. That's its equivalence. All right, our second word is going to take that word equivalent, which we could use outside of math, and we're going to make it specifically math related. And we're going to do that by defining an equivalent expression. And we're going to have 2 different definitions for this one. But the first one is expressions which obtain the same value when substituting the values of the variables. So 2 expressions are equivalent when you can plug in the same values for like a variable x or y, and you get the same amount in the end. So for example, number 1, let's say we have 2 expressions. So if we had 2 plus 5x, and we had separately 5x plus 2. If we want to figure out if these are equivalent expressions, we can always plug in an x value. So let's let x equal 0. When we plug it in, if we get the same value for each, that means they're equivalent. And this should work for every single x value. But specifically, if we're saying let's let x equal 0, 5 times 0 is 0, so you get 2 plus 0, which is 2. 5 times 0 is 0 plus 2, you get 2. So these are the same. So that means that they are equivalent expressions. Now we only did where x is equal to 0, but in order for us to say they're truly equivalent, it has to be for every single value of x, and it is in this case. And we know that by looking at our original expressions. So if we have 2 plus 5x and 5x plus 2, we know by the associative property that it doesn't matter what order we add them in, they will still be equivalent. Okay, so let's move on to our second definition, which is expressions that are equal to each other no matter what the condition. So we just talked about this with our first example. 2 plus 5x and 5x plus 2 are the same. We've just switched their order. But by the associative property, I'm sorry, I forgot my properties there for a second, of addition, that is still going to be the same thing. So they're still equivalent. However, we use the second definition a whole lot more. So expressions that are equal to each other no matter what the condition. For example, number 2. Let's say we start out with the expression 4x squared minus 2, and they tell us when x equals 1. It's telling us x equals 1, so that means that we're going to plug in that x, that 1 value every time there's an x. And so we can plug it in, so let's do that. We get 4 is 1 squared minus 2. Okay, and then I can simplify that. So 1 squared is going to be 4 times 1 minus 2. And if you notice, in between my first expression and my second one, I put an equal sign. The reason I'm putting this equal sign is to kind of keep track, like this is separate from this, I'm not going to combine it all together. But it's also saying these are equivalent expressions. I've just moved one step in simplifying it. So when I put that equal sign, I'm saying this is equivalent to this. They may look different, but it's only because I've simplified them. I haven't changed their value. So if I continue on, order of operations, 4 times 1 is 4. And then minus 2, you get 2. So all of these equal signs in between the process of solving it tell us each of these is equivalent. So this is one long equivalent expression train. And this brings me to my last example for number 3, and you should be taking up the space for the number 3 vocab word. So example number 3 says factor completely, and then it gives us 3p squared plus 24p plus 45. So we need to factor this. Remember, factor means breaking something up into what we multiplied to get it. So if we're looking at these 3 terms, 3p squared, 24p, and 45, think about 3, 24, and 45. We can take a number out of all of those. We can take a 3 out. So let's go ahead and put an equal sign, because what we're about to write is an equivalent expression, and we want to keep track of it. So we're going to take a 3 out of all of these terms. If I take a 3 out of 3p squared divided by 3, it's just p squared. 24p divided by 3 is just going to be 8p, and 45 divided by 3 is going to be 15. So think about, the reason this is an equivalent expression is if I foiled this, or I'm sorry, if I distributed this, not foiled, then I would get back to the original. These are equivalent. They don't look exactly the same, but they're still equal. So I can keep factoring this because the 3 is going to come out, but we have all this stuff left over on the inside. They can still be factored. So we can either use guess and check, or we can use the AC method, but we think about what can we multiply to get 15, that'll add or subtract to get 8. We know it's going to be a binomial times a binomial, and because this is a p squared with a 1 out in front, it's going to be p times p in order to get p squared. And we can multiply 5 and 3 to get 15, and those will add to get 8. So the fully factored form of this is 3 times the quantity p plus 5 times the quantity p plus 3. And if we've done this correctly, which we have, this factored form is equivalent to the original. All we have to do is multiply it, and then we get right back here. Each of the equal signs that we use when we simplify is saying this is an equivalent expression to what just came before it. Okay, our third vocab word, but it's in the for space, is express, and this is as a verb. So to express something is, in mathematics, to change an amount or quantity into a different and still equivalent form. We already talked about equivalent. Express is another way to say we're going to change this into an equivalent form. So we talked about equivalent expressions and equivalent. Now let's kind of do a question that'll hopefully help make this a little bit clearer. Our example is a multiple choice question. It says, which polynomial expresses the difference of the two polynomials? So we've got two polynomials here and they're being subtracted. Remember, it's difference. And we want to know which one of these two answer choices expresses the difference. So basically, expresses in this means which one of these choices is an equivalent to this one. So let's go through it. I'm going to use a different color to do my work. And if I think about this, okay, so the 6 plus 5a squared is going to stay the same. Nothing's really affecting it. And as tempting as it is to think that these parentheses mean multiplication, the subtraction sign in between means we're going to subtract whatever's in this parentheses from this. So we need to distribute that negative to both the 8a squared and the negative 1. So it's going to become minus 8a squared and then plus 1. And now, if I gave you this separately and told you to simplify, you'd know what to do with this. You're going to combine like terms. So we have 5a squared and negative 8a squared, which becomes negative 3a squared. And then we have 6 and 1, so plus 7. So our correct answer is A. Okay, our number 5 vocab word is a rational expression. And rational is a fancy term for fraction. So a rational expression is a fraction in which the numerator and the denominator, or the numerator or the denominator, are polynomials. So basically that means it's a fraction with variables in it. So for our examples, number 1 and 2, example number 1 is x squared minus 1 over x squared plus 5. So I have two binomials and I've put them into a fraction form. So fraction with variables in it, it's a rational expression. My next example is 6 over z plus 2. So we have one variable, but if you notice, the numerator does not have a variable in it. It's still a rational expression because it's a fraction with a variable in it. Okay, the next vocab word is narrow, and you can use this outside of mathematics, and it still has the same definition. So narrow means of slender width. So if space is narrow, that means it's not as wide. So for example, if I draw two different graphs, and these are going to be on the same scale even though they aren't listed. If we look at graph A, it's wider. There's more space in between the two sides. Whereas B, it's got less space in between. So that means we can say that graph of B is narrower than the graph of A. That's because graph A is wider than the graph of B. All right, our last vocab word seems a little silly. It's define, especially as we're writing definitions right now. But we're going to talk specifically about the meaning that it has in mathematics. So we already know the meaning to give the meaning of. But now we're going to talk about the second, which is to mark out the boundary or limits of. So if I say I'm going to define the rules of the classroom, that means I'm going to tell you what's acceptable behavior in my classroom and what isn't. So that way I've defined the rules. So in math, our example is to define the equation of an absolute value function shifted up 3 units and right 2 units. So in this case, define, it doesn't mean it wants to give us the definition. It means it wants us to tell what the equation is. It wants us to define it, to figure out what it looks like. So if it's an absolute value function, that means our parent function of the absolute value is going to help us out. And the parent function is f of x equals the absolute value of x. So we know it's going to be based on the parent function, and it's going to be shifted up 3 units. So if it's up 3, up and down means it's happening outside the function, and up 3 is going to be plus 3. I have no idea why I just wrote 5. All right, and right 2 units, right or left means it's going to happen inside the function. So we need to rewrite this a little bit. It's going to be f of x equals, and then something's going to happen inside the function. We still have that plus 3 outside, but the x is going to be subtracting 2. So if it's moving to the right, that means it's going in the negative, or I'm sorry, it's going in the positive direction, but it's going to be a negative inside of the function. The equation f of x equals the absolute value of x minus 2 plus 3 is that function defined. We have defined the equation of an absolute value function shifted up 3 units and right 2 units. This is what the limits are. This is what the boundaries are. If we gave that to someone, we could graph it and we'd get the correct graph. All right, students, that's the end of vocab for today.